Begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for these students. Just pray you be with us today. Help us to just understand a little bit more about limits and all that, and just how to understand them, Lord. In your name I pray, Lord Jesus. Amen. So let me remind you, so we're talking today about limits and continuity. Let's say in Rn, but really, for the most part, we're going to either be doing n equals 2 or n equals 3, truth be told. But I think, I don't think I even asked you one homework problem of this nature. It would be a healthy thing for us, since some of you are math majors, it would be a healthy thing for us to remind each other what the definition of the limit was in Calculus 1. So let me remind you. If for each epsilon greater than 0, there exists delta greater than 0, for which 0 less than the absolute value of x minus, let's say a, is less than delta, implies that the absolute value of f of x minus L is less than epsilon, then the limit as x goes to a of f of x is equal to L. So that's the so-called epsilon delta definition of the limit from Calculus 1, right? And how about continuity? How did we define continuity of a function at a point? Do you guys remember that? Let me review that briefly. Definition. For a in the domain of f, we say f is continuous at a if the limit of f of x is equal to f of a. And, well, let me just put some, where this is, either double-sided or left or right as appropriate, all right? As appropriate. For example, if we're discussing the continuity of the square root function, right? So like example 1, the limit as a approaches 0 from the right of the square root of x is equal to 0. The limit as x approaches a of the square root of x is equal to the square root of a. So that's a right limit, and the other one is for a not equal to 0. Right? So just to remind you, we can draw a picture, basically what's going on here, right? Square root looks like this. And so if I wanted to picture what's going on, so here we're going like that, right? We're approaching like that. Here we're approaching it from both sides, right? And basically, the continuity of the function, if you just want a quick, intuitive reminder of what it means, it basically just means that the values of the function, right, they're not jumping at the point in question. Yeah?
Would that be the limit as x approaches 0, am I right? And example 1?
Oh, yes, thank you. Goodness gracious, what's wrong with me? Thank you, Shane. Very, very helpful. Scheduling my class at 8:15. It does do things. So anyway, this is, of course, a limit, the definition of limit, and what we mean by continuity in Calculus 1, right? Now, you may or may never have seen this epsilon delta definition before. I'm told if you took Calculus 1 here, you've seen it, but you've not done much with it. And depending on who you have, right? But now the question then is, so just to put this in words, what this is saying, so this right here is what? This is the distance. See what this is, what this says? Let me put it into words. This says that the distance from y equals f of x to y equals to L, right, is at most, well, it's less than, rather, less than epsilon units, right? What's this inequality say? This says that you're within delta units of A, but what does this down here say? If 0 is less than that absolute value, that means you can't have 0 equal to the absolute value in our like precondition for x. So that means that x is not equal to A. And this is how we calculated limits, right? You consider points close to the limit point, but not actually at the limit point, right? Unless you're studying continuity, in which case you got to plug the limit point in and it better work. Now the lion's share of examples, we can actually just plug the limit point in, right? Except when? What is the, like, the most important example of indeterminate limit in Calculus 1 is what? Do you guys remember indeterminate forms? What were they? What were the indeterminate forms? Do you guys remember? There's like seven of them. 0 over 0, infinity over infinity, infinity minus infinity. Very good. What's the other indeterminate type? 1 to the infinity. 0 to the 0. Yeah. Infinity to the 0. Right? What else? You guys missed one of the easy ones. What's that?
Infinity plus infinity?
Infinity plus infinity is just infinity. Yeah. That one's easier. It's kind of like infinity over 0. That's just big. Right? It's not indeterminate. It's just blowing up. How about 0 times infinity? That's one. Right? That's another. That's oftentimes how it comes to you. Right? These are your usual indeterminate forms. If you have a limit which has this pattern, what does that mean? It means that you have to do algebra or, you know, use the squeeze theorem. You got to make some kind of argument to take it from what you have to something that you can understand, right? And saying that these are indeterminate forms is to say that if you have a limit with this pattern, it could work out to anything. It might not exist. It might work out to 1. It might work out to 2. It might work out to infinity. Who knows? All right, they're indeterminate, which isn't to say that they're not determined eventually. It's just to say in their present form they couldn't be determined, right? Okay, so anyway, that's just a brief review. So how are we going to define the limit for a function of several variables? See, because now we're thinking about, we consider a function of x and y, right? Or you might even think about a function of x, y, and z, right? Or you might even think of a function of n variables. So now we want to imagine a function of 2 or 3 or more variables. How are we going to define the limit in this context? All right? So I'm just going to define it in Rn, and then maybe we'll specialize to like 2 or 3 dimensions then. But here's the definition in Rn. If for each epsilon greater than 0, there exists delta greater than 0 for which 0 is less than the length of the vector x minus a. Now, I guess let me not use this notation because this is calculus 3. I put vectors on vectors, right? I put vectors on vectors. So let me put vector, I'm talking about, and I won't use x, I'll use r, because we usually use r for the position vector. So like r vector and a vector less than delta implies, now what I just wrote in red, the line above, I'm still thinking of all of these as just being a real valued function of a real variable, all right? Well, it's a real valued function of several real variables generally, but my point is what's in red, I'm just thinking about it being real valued. So to understand closeness of the output of the function, I can still just use absolute value. So I just have implies absolute value of f of r minus L is less than epsilon. Then the limit as vector r goes to vector a, which is a point, all right, of f of r is equal to L. Let me just specialize this for 2 dimensions for a second. So like in 2 dimensions, this would look something like 0 less than, the square root of x minus a1 squared plus y, or I could do ab, x minus a squared, y minus b squared less than delta implies that the absolute value of f of x comma y minus L is less than epsilon. Then the limit as x comma y goes to a comma b of f of x comma y is equal to L. So that's what the definition in 2 dimensions, the second sentence of it looks like in detail. Yep.
In 3 dimensions?
2.
Because you have x, y.
We refer to the, I'm referring to the domain when I talk about the, so I'm talking about, when I talk about the dimension of the limit, I'm referring to the domain of the limit. So while you looked at graphs in 2 dimensions, you've only so far considered 1-dimensional limits, because I'm speaking of the domain. So calculus 1, x approaches a. You could approach from the right, you could approach from the left. You could even go to plus or minus infinity, right? But anyway, so do you guys want to tell me like geometrically what this means, what I wrote in purple? Let's like think through it. What is this saying? This right here says that if you look at the point AB, right? What is this condition? 0 less than the, this is the distance from the point xy to the point AB, right? So if you want to picture that, what you're looking at is like a little delta ball. Well, delta disk really here, right? The disk of radius delta, right? The disk of radius delta. And what else have we done? We have deleted the center point from it, right? We don't actually consider the limit point. Okay? So let's look at some examples. Example 2. How about if we have the limit as x comma y goes to 1, 2 of x squared y minus x over y. And listen, I'm going to be somewhat lazy in here, guys, and I'm just going to use words. Guess what? For the multivariate limit, we have limit laws. All right? What are the limit laws? Limit of a sum, sum of the limits. Limit of a product, product of the limits. Limit of a quotient, quotient of the limits. Limit of a composite, composite of the limits. Assuming what? What's the strings attached to the limit laws? Remember? We have to have that the limits that you're breaking it up into, that you're applying the laws for, they exist, right? So the limit of the sum is only the sum of the limits, in as much as both of the things you're adding have existent limits. How about here? What if you plug in 1, 2 into this expression? What do you get? We get 1 squared times 2 minus 1 over 2. And there you go, 2 minus a half, 3 halves, happy day. All right. What would we mean by continuity for a function of several variables? So I'll give you the n-dimensional definition just to be lazy. F, a mapping from Rn to R is continuous at A if the limit as R vector goes to A of f of R equals to what? trying to define continuity. If there's any justice, it should coincide with the definition of continuity we had in Calculus 1, right? So what should continuity of a function mean? It should mean when we take the limit at a point, we can just do what? We can just evaluate to calculate the limit. So this is just literally f of a. There you go. That's the definition of continuity of a function of n variables. Excuse me. So like, theorem, which I will not belabor in here because, this is not the time or the place to do it, but theorem, multivariate polynomials are everywhere continuous. What's a multivariate polynomial? Well, my example 2 is an example of a multivariate polynomial. A multivariate polynomial is just when you have a sum of powers of several variables. Like, rather than further clarifying what I mean by the terminology, let me further clarify the meaning of the terminology with an example. All right? I hope you like this example because it's going to be our only 4-dimensional example from today, but here goes. If we have the limit, now I'm going to let you guys, we usually use x, y, z for the Cartesian coordinates in 3 dimensions. What should we use for our 4th Cartesian coordinate in 4 dimensions? Do you want to add one before x or one after z? Where do you want to go? Sigma? Well, I wasn't expecting that. I'll put that one last. So x, y, z. No, I just can't do it. No, it's got to be a Latin letter. I can't abide this sigma. No, I'm sorry. I'm sorry, Sam. It's okay, but I can't do it. Typically, people add a t for time because you think about space-time being 4-dimensional. Or you can add a w at the end. Whatever. I'll put a t at the start just to be there. Now it's time-space. T, x, y, z. All right, so if we had, for example, x squared plus y squared plus, y t x, y t z, this would be an example of a multivariate polynomial. Does that make sense? Multivariate polynomial is nothing to be scared of. It just is like a polynomial, but with more than one variable. All right? And to be clear, I need to make this approach at some point. Let's make it approach 1, 2, 3, 4, just for the sake of, easy tracking of things. So that means I put x equals to 2. I put y equals to 3. And then my y was 3. My t was going to 1. And my z was going to 4. All right? So you got 4 plus 9 is 13. 13 plus 12, 25. So, goodness gracious, if I had a question like this, like as problem 1 on the next test, if any one of you misses it, I have to kill you. Like, I have to literally murder you. Don't make me do that. I don't want to do that. There's this professor at NC State who used to teach business calculus, and he was well known in his class to tell students, like, after you take my class, I come up to you in the hallway, and you say, oh, hi, Dr. Chu, and you're like, and you see me, and then I say to you, what is the fundamental theorem of calculus? If you can't answer me, I kill you. He's well known for saying this. This is a while ago. This is really before the age of the internet. He was already posting his faculty picture as like a selfie. Like his faculty picture is from like a handheld digital camera held like this, looking at you. So he may have invented the selfie. I don't know. May have. Hilarious guy. All right. Anyway, so these kind of limits are not hard, right? But what about? Let's look at something a little bit more delicate. Something like, I'm looking at it from the book because that will help me. Come on, come back. See, if I just make up stuff, it'll be bad. So let me phone a friend here. This is an example from the textbook, believe it or not. You're like, what? An example from the textbook? No way, dude. All right, so here we go. Limit of xy approaching 0, 0 of xy squared over x squared plus y to the fourth. So by the way, I should tell you a theorem. Theorem. If the limit as r goes to a of f of r is equal to L, then the limit as t goes to 0 of f of r of t is equal to L for all paths t maps to r of t for which r of 0 is equal to my given point. So this is the theorem is simply this. If the multivariate limit exists, then all quote-unquote path limits must exist and agree with the limiting value. So here, t maps to r of t is like a path. All right? So in example 4, what's the problem here? Well, this is the quotient of multivariate polynomials, right? Which you could say is like a multivariate rational function, if you like. But the trouble with this is we've got what? What happens when you plug in 0? Upstairs you got 0. Downstairs you got 0. It's type 0 over 0. So what are we going to do? Well, in the multivariate case, what you typically want to do is look at path limits. All right? Okay, basically there are just two things. Fine, four things we can do. Number one is it's continuous. Woohoo! Plug in the point. Done. I like those. That was my example 2 or 3. All right? That's the easiest thing. I started with that. You're welcome. Number 2 is we could try like a squeeze theorem argument. Right? You have this, the squeeze theorem. If you can show one thing is less than the other is less than the other, and the two things on the end obviously go to something, then the thing in the middle must also. So you can make that kind of argument also. I don't think I have one of those to show you today. And then the third thing you can do is you look at it, it's indeterminate, right? And you decide maybe this thing doesn't have a limit which exists, right? If the limit doesn't exist, then maybe, just maybe, you can look at different paths. And by looking at different paths, you find different limits. If you get different limits from different paths, game over, the limit doesn't exist. Because if you go the other way, right? If there's even one path limit, if there's even two, if there's even one path limit which doesn't exist, game over. If there's even two path limits which don't agree, game over, the limit doesn't exist, right? Because if the limit did exist in the multivariate sense, it implies all of the path limits have to exist. You've seen this theorem before in Calculus 1. In the double-sided limit, what are the path limits? There's only two. Basically, there's either from the right or from the left. Well, whatever your right and left is, but anyway, you get the idea. That's a slight abuse, but okay. So what are easy paths to look at through the origin? How about this? How about lines through the origin, right? Lines through the origin, like this, right? Whee! These guys, yeah? So you could think about y equals to mt, x equals to t. If I want to stick with my t variable, just to try to be consistent in my notation for once in my life. So if we consider these paths, the limit as t goes to 0 let's see here. I'm going to put x equals to mt. Excuse me, my bad. X equals to t. Y equals to mt. I'm supposed to square that thing, right? And then I divide by t squared plus mt. Uh-oh. I feel a cough coming on. To the fourth. You guys do algebra while I get candy. Do you guys like limits? Because we're going to spend like the next 3 weeks on limits.
Sounds lovely.
That was a lie. This is the only day we're spending on limits. Tomorrow we'll be moving on to partial derivatives. So, yeah. There is a way to stretch this material out and make it last a week, but that's not what I'm going to do. So, I think limits are like a Band-Aid. You need to rip them off. Just rip it off. Be done with it. Okay, so. I mean, assuming the Band-Aid's already served its purpose, you know, of course. Sure. Main purpose of Band-Aids is to make children stop crying. Let's see here. So we got ourselves a m squared t to the power 3 divided by t squared plus m to the fourth t to the fourth. Now this limit is a one-dimensional limit with a variable m in it, right? I'm considering a line of arbitrary slope m, all right? So then what? Can you simplify this? We can divide by, I think we should divide by t squared maybe. That'll do the trick. So limit as t goes to 0 of m squared t divided by 1 plus m to the fourth t squared. Rats! I got this out of the book. Please let me have copied it down wrong. Come on, phone. I mean, it's not, what we're doing is not wrong. It's just, this does not tell us. This doesn't give us any information. What does those limits work out to?
0 over 1.
Yeah, 0 over 1, which is what? Infinity. No, 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 no. Infinity? You guys are killing me. It's just upside down. So the numerator works out to 0 for any finite m. We only think about finite m. Downstairs, I get 1 plus 0, also known as 0. 0 over 1 equals 0. It's not an indeterminate type. This is just 0. The limit just works out to 0. So unfortunately, this doesn't give me any information about the ultimate demise or lack thereof of this limit. So we need to try something a little bit more sneaky on this one. My apologies, guys. I was trying to lead with the example that the looking at the lines through the thing give you different values. But what has happened is that I've taken pictures in my phone and I've forgotten the reverse chronological aspect of taking pictures. So looking at my pictures, I found example 3 before and I found example 2. So anyway, this is easily fixed. What we do is instead of looking at lines, there are other paths through the origin, you see. There's also parabolas, right? So we're still on example 4, but let's look at all possible parabolic paths, right? These would be y is equal to, like, you know, kt squared, and x is equal to t, right? Now, if you like, you see that if you wanted to, you could replace t with x here and look at the limit as x goes to 0. That would be the same. I'm sticking with t in the interest of, you know, notational consistency here at the moment. So we look at the limit as t goes to 0 of so x, still that one, x, so x is t. Now y is kt squared divided by t squared plus kt squared to the fourth power. All right. Man, I hope this works. If this doesn't work, I'm gonna be sad. Oh man, that's not gonna work either. I don't think. Rats. The annoying thing is I took the picture of the start of this example, not the whole example, so I don't remember what happens. See what happens here? This is the same song and dance, right? We get limit as t goes to 0. I get, oh, maybe I can resurrect it. No. All right, so this is, what does it give us? This gives us k squared t to the 5th divided by still t squared plus k to the 4th t to the 8th. That's not making anything better. We divide by t squared. What do we got? We've got k squared t cubed divided by 1 plus k to the 4th t to the, I divided top and bottom by t squared, so I get t to the 6th here. So again, this is equal to 0 as long as k is not equal to 0. I mean, even if k is equal to 0, it's still equal to 0. So it just works out to 0. Oh. What? Yeah.
Is there any way that you could like see that since positive values would actually give you positive values for the whole thing, negative values would give you negative for the whole thing?
But they work out to 0. I mean, you can have positive on one side and negative on the other, but if they all squeeze to 0, it's still, the limit's still 0. So that alone is not damning. Well, let me show you my other trick. So this, I think maybe if we look at all like the, like, we might need to look at like, anyway, let me not waste too much more class time with this one. I mean, I will figure out how to solve it and tell you if I haven't figured it out right now. Let's see here. The other thing you can do, though, is you can change to polar coordinates. You can do a polar coordinate substitution. That might do it. That might allow us to see it. By the way, this is example 3 in the textbook, so if you want to read the textbook after class and find out what the resolution to this paradox is, you can do that. I'm just too lazy to walk back to my office and get the book, so my apologies, but it's so far away. And also, this is good for us, actually, to get stuck on something. See here, so, well, I wouldn't say we're stuck, but I would say that the methods that I'm employing are not being fruitful, right? They didn't help us this time. I'd like to show you how they help, though, so we'll have to get past this example. But polar substitution, if you're going to the origin, right, what can you replace xy going to 0 geometrically with? Think about it. Yeah, we could just replace it with the limit as r goes to 0, right? And we just plug in x equals to r cos theta, y equals to r sine theta. Now, if this one also doesn't work, I'm going to be really annoyed. So we've got ourselves an r cos theta, r sine theta. You square that thing, right? And divided by r cosine theta squared plus r sine theta to the power 4. Let's see here. We've got the limit as r goes to 0 of, well, drats. I'm starting to think this thing converges. Cosine theta, sine squared theta, divided by r squared cosine squared theta plus r to the 4th sine to the 4th theta. I guess that's an important life lesson to learn. If you're trying to show a convergent integral, excuse me, a convergent limit diverges, it's going to take you a really long time, right? Pretty much until you make a mistake and convince yourself that it diverged. So if I divide by, let's see here, what can I do? I think I'm going to divide by r squared cosine squared and see what that works out to. That might be helpful. So I have r, I guess I'll leave the cosine theta downstairs, but I'd have r sine squared theta divided by cosine theta plus r squared, sine to the fourth theta. Well, if I'm not sure, I'm going to leave the cosine squared there actually. Sorry guys, I'll make up my mind eventually. So I'm just clearing out the r. All right, so let's think about some different things. If we put theta equals to 0, we've got what? Limit as r goes to 0 of what? That's a good question. Thank you. In the marker. So sine of 0, cosine, sine squared of 0, cosine of 0 divided by, let me just go ahead and evaluate. What's cosine of 0? Cosine of 0 is 1, right? And what's sine of 0? 0. So we've got, so this works out to 0. How about if we try like pi over 2? So think about this. What we're doing really is we're looking at paths. This is just, again, looking at path limits, but in the polar sense. We can examine rays, right? This is looking at ray limits using polar coordinate technology. So, well, look at that. That's 0 upstairs, and downstairs you've got 0 plus, well, no, but it's exactly 0 at pi over 2, so, So this is also equal to 0. All right, guys, I have to look at the book. I'm sorry. Well, actually, anybody happen to have their book on them? Put me out of my misery. So let's look at another example here. Oh, you don't have it? Or ebook? Wow. So let's look at example, while you guys are finding that. Example 5. Aw, man. I thought for once I was going to give a perfect lecture on limits. I mean, perfect for me, not, perfect, but only God can give a perfect lecture. Let's see here. All right, so we're at example 5. So did you guys find the book yet? X equals y squared. So x equals y squared. So let's see, if we look at the limit. So the other way to do path limits, you guys, is just to put the formulas into the xy. So like, so you do like y squared comma y maps to 0, 0 is the other notation for this. So in other words, put x equals to y squared. So if we put x equal to y squared, we get y squared divided by y squared squared plus y to the 4th, right? So in purple down here, the path limit. How does that work out? Man, these things are nefarious. So we're looking, what this would be is looking at a particular, this is just like the plus or minus the square root function, I think. Right, this is, if you think about this, this is y is equal to like plus or minus the square root of x, I believe. So it's coming into the origin like this, right? This, which is a different kind of approach than we've considered either with our lines or with our families of parabolas, right? Man, it doesn't seem like it should really do anything different, but look at what it does. So this simplifies to the limit. This we can simplify simply as limit as y goes to 0. That's really what we're looking at. And we've got y to the fourth over y to the fourth plus y to the fourth, also known as divide by y to the fourth, you get a half. So we get a half along this limit, but what have I shown every other different which way from Sunday? Like you can get 0 from many other paths, right? Any possible stupid line through the origin gives a limit of 0. Any possible parabolic path through the origin, in this sense, in these family of parabolas, gives us a limit of 0, right? Any possible ray through the origin, of course those are the lines, we already covered that geometrically, gives us 0. Yet, when we approach the origin like this, or like that, maybe I'm doing that wrong.
Should that be just a sideways parabola?
My bad. Yes, it's a thank you. It is a sideways parabola. But you know, when we approach like that, a half. And if instead of just looking at one of these, if you threw a parameter into here like a k, you'd be able to show that you could get any value you like by looking at these parabolic paths, not just a half. And then that means the limit does not exist. That's the conclusion here. Therefore, this limit does not exist because we found path limits going to 0 and 1/2. And of course, 0 is not equal to 1/2. All right, let me get my notes out here for a second and project for a bit. I do have some nice examples in the notes. So what do you guys, so I actually like the polar substitution a lot because the polar substitution, guys, it has the hope of showing the limit exists and it's equal to something. The path limit thing, it's like the work of a philosopher, right? What does the work of a philosopher do? Does it build people up? I think no. I think mostly, at least when I took philosophy, the whole class was just, it was just thing after thing after thing of tearing other people down. Like that's my experience. It's like it's all just, that doesn't even make sense. That doesn't exist. You know? I mean, I'm sure there are constructive philosophers, but I didn't take a class from one. So I can only tell you about what I experienced. So, and if you're not a math major, you can skip over this epsilon delta stuff if you want to. Like, it doesn't matter, guys, okay? So here is the example I should have started with. Duh. See, here we have 2xy over x squared plus y squared. And if we plug in AB not equal to 0, fine, it's continuous there. Just plug it in, done. Whee! But at 0, we got problems. And so what I did here was I looked at the path limit t comma mt. In other words, x equals to t, y equals to mt. Those are lines through the origin. When I shove that into this formula, I get that constant, which just is this. But then the thing is, for different slopes, that's different numbers. Therefore, the limit at 0 does not exist. That was what was supposed to happen in the last 15 minutes of class, all right? So my apologies. There it is. Here's a picture of why it's happening. So right here is a picture of the surface we were just taking the limit of. So we were, as you approach the origin for this thing, depending on which line you look at, they tend to different values. And so I've got pictures of the different lines of approach and the different values that they go to, in as much as the, so you can literally see the line of approach. Well, I maybe literally see is a little bit too strong, but if you trust your digital imagination there. This next example is the evil example we just got stuck on, right? Maybe. And in this one, if you feed a line into the function, they all go through 0. And here's the line, like it goes through 0, that one goes through 0, that one goes, all the lines go through 0. So that doesn't help. See that it doesn't exist. But you see, if we pass through these parabolic paths, right, then the parabolic paths, they, as you can see, I put the coordinate axes in red, I think. So the path limit, the values of it, where they are, in like the z versus xy is red, is green, is yellow. As you can see, when we go through the parabola through the origin, we get different outputs at the limit point, which is why the limit doesn't exist. There's actually a jump in the graph at the origin. It's like a tear. So there's that. Now the first example that I wanted to do, if you do that in polar coordinates, it's exceedingly obvious that it doesn't exist, because check this out. If I put in polar coordinates, right, the limit at the origin becomes this. The r squareds cancel. 2 sine theta cosine theta. So this is manifestly dependent on theta, right? You choose different theta paths, you get different limits. Therefore, the limit doesn't exist. So polar coordinates is like a very nice way of reasoning through these. What if you had a function with 3 variables? Let's see if I can find one. Oh, this is the squeeze theorem argument, if you care. And here's a 3-dimensional one. In 3 dimensions, if your formula is nice, you can use spherical coordinates and convert a limit at the origin to limit as the spherical radius goes to 0. And if it's made up to exhibit L'Hopital's rule, then you can use L'Hopital's rule, like differentiate, and you get that. It works out to 0. And here, actually, I've shown that this indeterminate limit, and 3-dimensional indeterminate limit, actually exists by switching to spherical coordinates, applying calculus 1 limits, and working it out. So listen, as I said, you could easily spend 3 weeks on this material. I do have some additional examples over here I'd encourage you to read through, but that's pretty much all I got to say about this. So tomorrow, partial derivatives, woohoo! And hopefully I'll have your test back.